acid-base equilibrium. Today we're going to be mainly talking about acids and bases and how we can determine if it's an acid or base from the structure. Let's start off by reviewing a little bit of information from Unit 2. Back in Unit 2, do you recall that unit? Yeah, maybe. Alright, so we talked about electrolytes. Strong, weak, non. Okay. What are some things you remember about strong versus weak electrolytes? Yes, strong acids. Strong acids and strong bases are strong electrolytes. And why are they strong electrolytes? Can you be more specific? They dissociate completely in water. Okay? What about weak acids and weak bases? They are weak electrolytes, and that's because they're only partially dissociating. We're coming back to that concept. Okay? So, the reason why weak acids only partially dissociate is because they have, we're going to be talking about this more next class, but they have relatively low equilibrium constants, Ka and Kb. Those are new-ish terms to you guys. You're used to saying Kc or Kp, but Ka just means it's the equilibrium constant for an acid, and Kb is equilibrium constant for a base, right? Okay, so weak acids and weak bases, they partially dissociate in water. So they're mainly going to stay together as a whole molecule, and we'll have a few of the ions actually forming. But let's just practice writing dissociation equations of different types of substances. Okay. So for this first one, HF, is that an acid or a base? It is an acid. How do you know it's an acid? Because it starts with hydrogen. That's typically an indication that it is an acid. Now, is that weak or strong? He said weak, and then everyone was giving me confused looks. He's right. It's a weak acid. And the reason it's weak is because there's only 3 binary strong acids, and that is HCl, HBr, and HI. You should know that HF is a weak acid. On your Unit 2 test, that was a concept tested in multiple locations. There was a multiple choice question about HF being a weak acid. Then you saw it in like 2 different locations in the free response, and that was like the most commonly missed theme across the board. People kept telling me HF was strong. It's weak. Okay? So, that is a weak acid. All right. So since this is a weak substance, when we write its dissociation equation, we're going to use that equilibrium arrow to demonstrate that it's only partially dissociating. Okay? And I think when I taught Unit 2 stuff, I used an equilibrium arrow for weak substances, and I said, we'll explain why later. It's later. We're at that point now. Okay? So what does this substance dissociate into? Yep, H plus and F minus. Cool? Questions so far? Pretty easy, right? They are technically aqueous. I'm not too worried about states of matter because it's not going to come into play until we start doing equilibrium expressions, which is next class. And really, most of our stuff is going to be aqueous, unless it's water. But ignore what I just said, because in this example, we have water that's aqueous. But later. Okay. The next one. Is that an acid or a base? Acid. It starts with hydrogen. Typically, things that start with hydrogen are acidic. And is that weak or strong? It is a weak acid. Let's review the rule of thumb for weak versus strong acids. What was the rule with hydrogens compared to oxygens? 2 or more oxygens compared to the number of hydrogens, right? Yep, and any acid that contains carbon is going to be weak. Because if it has carbon, then that makes it an organic acid, which all organic acids are weak. So since this is a weak acid, we're going to write the equilibrium arrow. And so what does that dissociate into? Exactly. I mean, it's not wrong if you say negative or minus. Questions? You should feel really confident with this. Good. All right, what about this next one? Oh, I wasn't paused. It is a base. So the rule of thumb for bases is it's always group 1 with hydroxide and then strontium and barium with hydroxide. So this, yes, this is a strong base. Now, strong electrolytes, remember, they're completely dissociating. So that means that the equilibrium lies very, very, very far to the right. In terms of equilibrium, they have very large equilibrium constants. So we're going to use just a single arrow because the reverse reaction really doesn't happen. Or the amount that the reverse reaction occurs is so tiny, it's so negligible. Okay? So what does that dissociate into? And? Yep. Cool. Feeling good about this? All right, what about LiOH? That is a strong base because it's group 1 with hydroxide. So what arrow are we using? Yep, a single arrow. Sometimes we might call that a strong arrow. Okay. What does it dissociate into? Good. Oh my gosh, my pen is freaking out. All right, Li plus and OH minus. That also would be an indication that that forward reaction is favored. Yeah. Okay. My pen's still freaking out over here. Okay, it's just going to dance on the page for you. All right, H2O. Before we try to figure out what it is, let's just write out the dissociation. I'm going to give it an equilibrium arrow. I'll explain why in a little bit. But if we were to dissociate that, what ions would it make in solution? H plus plus OH minus. So water we know to have what pH typically? 7, which means it is neutral. Water is neutral. Now, you might have learned in, actually, I meant to mention this later. I'm a little bit ahead of myself, but it's okay. pH less than 7, it's acidic. Greater than 7, it's basic. If it's exactly 7, it's neutral. You may have learned in previous science classes that pH of 6 to 8 is neutral, or like around 7. It doesn't have to be exactly 7. No, really, if neutral means you have equal concentrations of hydroxide and hydrogen ions, or hydronium. All right, so you have to have equal amounts, and that's only going to occur at pH of 7 when we're at 25 degrees Celsius. Yes, it is possible to have a neutral water with that's still considered neutral, but its pH isn't 7, and that's if you vary the temperature. We're not going to be dealing with anything not at 25 degrees Celsius. Okay? The textbook does go into that, and there's some practice problems in the back of the chapter to be like, hey, let's figure out what the pH would be if it's at this temperature. That's beyond the scope and sequence for what College Board wants you to know for the AP exam. But just be aware that if you go on to take other science classes in college, you might have to deal with when pH isn't 7. But we're not going to be dealing with any of that. Yeah.
This is part of one of the units in the Flim Prep that we didn't count, right? Like 9 or 10.
Yeah. All right. So water, I'm about to sneeze. Well, now I'm not going to. Thanks. So, water is a substance. Does anyone know the term amphoteric? Have you heard that substance before, or that term before? So water is amphoteric. And this gets us into a little bit about Bronsted-Lowry acids and bases, which is what we're going to be talking about in problems 4, 5, and 6. But water can act as an acid or as a base, depending upon what it's reacting with. Okay? That's because, and water auto-ionizes with itself. So really what happens, it's not what I have written here. Really what happens is water will react with itself and it'll auto-ionize, forming the hydronium ion and the hydroxide ion. And that's how we get to that Kw, that equilibrium expression for water and the equilibrium constant, which is on your formula sheet. I'll be reviewing that stuff in a little bit as well. But water will auto-ionize, okay? So if you have a pure substance of water, or a pure sample of water, you should have equal concentrations of hydronium or H+. In chemistry, we can use those interchangeably. Biology, not necessarily. But in chemistry, we use them interchangeably. So we have equal amounts of hydronium and hydroxide. Pure water, you'll have 1.0 times 10 to the negative 7 molar of each of those. And that's what gives its pH of 7. Okay? If it's reacting with a substance that has more hydronium ion content or hydrogen ion content, then water is going to act like a base because it's more basic. It's really just, it's all relative to each other. It's a scale. Okay? You can talk about the acidity of something even if it's a base, because you'd be like, oh, let's talk about its acid properties, or like it's more acidic than something else, but they can still be bases. Does that make sense? Okay. But water's amphoteric. We're going to come back to this concept about water being amphoteric in a little while. Then this last one, H2CO3. What type of substance is that? It is a weak acid because it's one of those carbon-containing acids. How many hydrogens does that substance have? 2. This is a diprotic acid. We are going to spend a lot of time, or not a lot of time, we're going to spend a few problems talking about diprotic, polyprotic acids, things that have more than one acidic hydrogen. Okay? A little bit of a preview into that. What ends up happening is when they dissociate one hydrogen at a time. They dissociate like stepwise. Okay? So our first dissociation equation would be taking off one of the hydrogen ions. What's left over if I take off one hydrogen ion from H2CO3? HCO3 minus. It's just minus 1 because it was originally neutral and we take off a positive 1. So it's HCO3 minus, which you should recognize as being the bicarbonate ion. Bicarbonate is also an amphoteric substance. So water is not our only amphoteric. Okay? So that bicarbonate can actually go either way. We'll talk more about that when we get to our diprotic section. This, like I said, this is just a little preview. So then our second dissociation would be HCO3 minus, wrong type of arrow, dissociating into H plus and what's the other product? CO3, yep, or 2 minus. Cool? Questions so far? Okay. So we're going to put a pin in this for right now, and we're going to review how to calculate pH and pOH and that type of stuff. So if you haven't already grabbed a calculator, you will need one for these next couple problems. So on your formula sheet, the majority of the formulas you're going to need to calculate pH and pOH are on there. Okay, so remember, equilibrium section is on the front, in like the middle. Equilibrium and acid base is lumped together on the formula sheet. Okay, so you probably were already using some of these formulas with your last test, and then there's a whole section about like the acid base stuff. pH equals negative log of H plus. pOH equals negative log of OH minus. Both of those formulas are on your formula sheet. And it also tells you the 14 equals pH plus pOH. So you don't have to memorize any of those. Okay? You just need to know how to use them. So for this first one, we are going to find the pH and the pOH of all of these. So we're given the H plus concentration for this solution. Which do you think we're going to find first, pH or pOH? pH, because we have the H plus. So pH equals negative log of 1.4 times 10 to the negative 3. Now, the sig figs are a little bit weird. Okay. How many sig figs does that concentration have? 2. It has 2 sig figs. Bless you. You stole my sneeze. That has 2 sig figs. Now, when you find the pH, you still need to show 2 sig figs, but it's not going to be in the same format that you might think it's going to be in. So go ahead and do that calculation if you haven't already. Oh, and what units do we report with pH and pOH? We don't report any units. It's kind of like the K values. KW, KC, KA, KB, none of them have units. So it makes it nice and easy. Concentration has units, though. All right, so what did you get as the pH? You get like 2.85, 3, something, right? Okay. We're going to report that as 2.85. I'll explain why. That still has 2 sig figs, though. Okay, because for logs, I'll write this down up here. Sig figs for logs. So remember, logs, it's like base 10. The number of digits after the decimal is the number of sig figs in your log value. So like here, we have 2 digits after the decimal, so that's our sig figs. Whatever comes before the decimal is telling you essentially the power of 10 that it was. Okay? Now remember, pH is a negative log base scale. So it ends up inverting the entire scale, which is why a low pH indicates a large H plus concentration relative to hydroxide. Okay? So whenever you're going backwards, which we will do in number 3, when you're given the pH or pOH, in order to get the concentration, you look at the number of digits after the decimal for your sig figs. Whatever comes before the decimal doesn't count for sig figs. Because that's like the inverse, or the negative power of 10 that it's going to be around there. Okay? Cool? All right, so now we know the pH. How are we going to find the pOH? Yeah, pOH is 14 minus 2.85, which we will maintain sig figs by keeping 2 decimal places. What's 14 minus 2.85? 11.15. Cool? Is this substance acidic or basic? Acidic, because the pH is it's less than 7. pH is less than 7, so therefore it's acidic. Cool? Why don't you guys do letter B on your own? Notice I give you OH, so what are you going to find first? pOH. So why don't you guys try that one? All right, what did you guys get as the pOH? Good, 6.682. We need to have 3 numbers after the decimal because we have 3 sig figs. What did you get as the pH? 7.318. So is this solution acidic or basic? Basic. I mean, it's barely basic, but it's basic. Okay. Now, one thing I want to point out, and I will stress this again later once we actually start calculating pH of acids and bases. Right now, we're just knowing if the solution has this concentration, is it, what would be the other pH or whatever, okay? But next class, I'm going to stress this again. pH does not necessarily correlate with strength of acid or base, okay? You can have a weak acid and a strong acid that have the same pH, okay? That strong acid's still stronger than the weak acid, but they could actually have the same pH. You would need to manipulate the concentrations of them in order for that to occur. You'd have to have a fairly concentrated weak acid compared to a fairly dilute strong acid for them to be the same pH, but it is possible. Okay? pH correlates to the concentration of the acid regardless if it's strong or weak. Strength has to do with that equilibrium constant, which is dependent on the structure of the acid or the base. Okay, so strength has to do with structure, really, but you can determine the strength from the K value. pH has to do with concentration. I'm stressing that importance because it is a common misconception, even with students who've already gone through the acid-base unit. Okay, so I want to make sure you understand that they're not the same thing, right? Okay. We're not going to do C or D of this. Let's just go on to number 3. This is working backwards from the given pH or pOH. Can we find the H plus and the OH minus concentration? Okay. Now, the formula for going from pH to H plus is not on the formula sheet. Okay, so remember, to go to pH, you take negative log of H plus, right? So what would be the opposite of that? If I wanted to solve for H plus, what would I end up getting? Ten to the, well, what do we do with that negative? Is it negative 10 to the pH? 10 to the negative pH. That's where the negative sign goes. Okay? You'll never have a negative concentration, all right? But that's where the negative sign goes because it needs to be a small concentration. Like I said, that formula is not on your formula sheet. You might want to memorize it. Or just use your calculator. The calculator, can I borrow yours for a second? The calculator, for a lot of these functions, the opposite one is the second function. Like that's why I like to do the opposite of x squared, you have to do second x squared. To do the opposite of log, you have to do second log, which is 10 to the x. Ooh, it's just where that negative sign goes that can be, that's the tricky part. So if that is the formula for finding H plus, the formula for finding OH minus is what? 10 to the negative POH. Ugh. Okay? So let's look at this first one. We're given that the pH is 7.41. How many sig figs does that have? 2. Just the 4 and the 1. The 7 tells us the power of 10, the order of magnitude. Okay? So to find the H plus, we're going to take 10 to the negative 7.41. And we'll have 2 sig figs. We'll have to actually calculate that out. Don't leave it like that. And we'll put the units back on the concentration. So what do you get when you calculate that? 3.9 times 10 to the negative 8. And what's our unit? It's concentration. There are units. Molarity, or you can do moles per liter. But you have to put units on your concentration. pH doesn't have units, concentration does. So now we want to find the OH minus concentration. So how am I going to find that? Yeah, we could do that. We could find the pOH. We could do 14 minus 7.41 and then 10 to the negative whatever that answer is. Or you can use the KW formula. This one is on your formula sheet. KW is always equal to the H plus times OH minus concentration. KW is the equilibrium constant for water. Okay? That is 1.0 times 10 to the negative 14, which again, it's on your formula sheet. Okay? So you will always know KW. In this case, we know KW and H plus, so we can find OH minus. So 1.0 times 10 to the negative 14 over 3.9 times 10 to the negative 8 equals my OH minus concentration, which is what? Yep. And the units? Molarity or moles per liter. Cool? Questions? All right, why don't you guys try letter C? Okay, notice I gave you POH to begin with, so what are you going to find first? OH minus. So try that one. Okay, now that you've had a chance to do this one, what did you guys get as the OH minus concentration? 0.589 units? Molar or moles per liter. And the H plus? Cool. Questions? Comments? Concerns? Cool. Good. That should have been really easy. That this was the level of the pH type calculations you were doing last year or whenever you took chemistry. Is anyone 2 years out in this class? You are? Well, you guys are weird. You're 2 years out? Okay. Because you guys took the 2-year integrated at AOS. Yeah. It literally was you. What, did the book just jump off the desk in front of you? You're the only one around it. I'm really glad I caught that on video. Okay, so now we're coming back to the structure stuff. Okay? Coming back to the structure stuff. So, for all of these acids, we're going to be writing what's called the conjugate base. Okay? A conjugate base is a substance that we've removed an acid from it. Or, sorry, not an acid, a hydrogen ion from it. So for all of these, we're going to take away one hydrogen ion. Okay? Let me show you for this first one. So H2PO4 minus, if we remove one hydrogen ion, it would become HPO4 2 minus. Do you see how I did that? Okay. You're being sarcastic. I thought you were just really excited. All right, so HPO4 2 minus. It's one hydrogen away. That's what's being called a conjugate. All right. What about for B? What do you think that would be? Okay. Yep, ClO2 minus. So not only are we taking away the letter H, but we're also changing the charge for all of these because we're taking away H plus 1. Okay? So the number of hydrogens in that substance decreases by 1, and the charge decreases by 1. Got it? All right, what about for C? What would be its conjugate base? OH minus. Now, for D. The hydrogens that are attached to the carbon are not acidic. Okay? So these hydrogens here are not my acidic hydrogens. Okay? What that means is, let's think back to some stuff that we learned in first year chemistry, whenever you took that. The carbon hydrogen bond is fairly nonpolar. I mean, it's kind of like the definition of nonpolar. It only has an electronegativity difference of 0.4. Okay, I don't expect you to remember that. Not yet, at least. But it's a nonpolar bond. That means that water isn't really able to separate it because it's like a pretty covalent bond right there. The more polar a bond is, the more easily water can separate those substances. Okay, because the more polar, the more ionic it ends up being. So here, NH3, or this nitrogen-hydrogen bonds, that's fairly polar. That's why water will dissolve, or why hydrogen bonding occurs within molecules that contain nitrogen, oxygen, or fluorine with hydrogen, because it makes a very, very, very polar bond. Okay, so this right here is my acidic hydrogen. So when I remove a hydrogen from this, I'm going to be removing from the nitrogen, not from the carbon. So for any organic substance, you'll never touch the hydrogens on the carbons. Okay? And that's one reason why carbon-containing acids are weak. All right, so if I take away a hydrogen there, the CH3 stays the same. And what's the rest of it? NH2. Cool. What about for letter E?
Oh, oh wait, no, that's not acidic, so it's just OH.
Well, how can I remove a hydrogen ion?
You
You can't! This is a trick question.
Aha, I beat the trick.
It's the only trick question I'm giving you today. What? All right, it's a trick question. That is not an acid. You cannot remove. You cannot remove that hydrogen ion. Okay? It is OH minus is like the definition of being basic. All right, it's like pretty much the most basic you can get. You cannot become more basic. Okay. All right. So, and then for F, what would be its conjugate base? NH3, which you should definitely recognize as being basic because ammonia is something that we use pretty much all the time. You should just know that NH3 is a base. Questions so far? Feel pretty confident about that? All right, why don't you guys figure out the conjugate acids for these bases. If the conjugate base of an acid is the product after removing a hydrogen ion, what is the product, or what would we do to write a conjugate acid from a base? Add a hydrogen ion. And none of these are tricks. None of these are tricks. So why don't you take a minute or two to figure out the conjugate acid formulas for these bases. So now that you've had a moment to figure out the conjugate acids for all of these, what did you get as the conjugate acid for OH minus? H2O. What about Cl minus? HCl. CO3 2 minus? HCO3 minus. Good. I'm really glad nobody said H2CO3 because that would be 2 hydrogen difference. Okay? A conjugate is only 1 hydrogen away. Kind of like derivatives and integrals. Like I know a lot of you are in calculus. If you had a derivative and its integral, you should be able to recognize, or maybe not a derivative and its integral, but like if you had an equation and then you had its derivative, you should be able to recognize that it is the derivative of it. Maybe then the second one. Yeah? See where I'm going with that? Okay. H2O, what is its conjugate acid? H3O plus. Yeah, I did not give you another trick. However, if I had given you H3O plus and asked for its conjugate acid, that would be a trick. Okay, because that's like the most acidic you can be. That's like the definition of being acidic. What is the conjugate acid for this substance? Good. And then what about this last one? Perfect. Questions? All right, so now we're going to kind of combine this with writing equations. Now, I was saying before that water is what type of substance? What was that word? Amphoteric. Water is amphoteric, which means it can act as an acid or a base. When water is reacting, when water is with, or let me back up. When you put a weak acid in water, it actually goes through what's called a Bronsted-Lowry reaction with the water, where water acts like a base. When you put a weak base in water, it goes through a Bronsted-Lowry reaction with the water, where water acts like an acid. So you really have to look at whatever water is with. So for each of these, we're going to react them with water. Okay? Now, this first example, I need to change for next year because I don't like that it's a strong acid, because typically, strong acids, we don't discuss its reaction with water because it just fully dissociates. But let's go through the motion just so that we can say, we can practice the concept. Okay? So when HCl reacts with water, HCl we know to be what type of substance? Yeah, it's an acid. So therefore water has to be my base. Okay. In a Bronsted-Lowry reaction, what happens always is the acid will donate a proton to the base. Now, what do I mean by proton? I mean hydrogen ion. Why can I use hydrogen ion and proton interchangeably?
Because hydrogen has a positive charge, which means it has one more proton than electron, which means it can donate its proton.
Okay, so H plus 1 is a proton because hydrogen, the hydrogen atom, has how many protons? 1, because its atomic number is 1. When neutral, how many electrons does it have? 1. And the majority of the isotopes of hydrogen have 0 neutrons. Okay? So, for the most of our hydrogen ions, it's H plus 1, so that means it's lost that 1 electron it already had. It has no neutrons, so all that's left is a proton. So I'm not changing anything about the nuclei in any of the atoms in my molecule. It's just, proton means H plus, which is why like diprotic acid, it's talking about 2 hydrogen ions that it can donate. All right, so here, like I said, we're going to transfer, or we're going to be donating a hydrogen ion from the acid to the base. That says donates, H plus. Okay, it's always going from the acid to the base. All right, so what are my products of this? If HCl gets rid of a hydrogen ion, what's left? Cl minus. And if H2O gains a hydrogen ion, what do we have? H3O plus. Now, we're almost done with this problem. Back here in number 4, all of these, except for E, all of these were acids, and we wrote the conjugate base. So the conjugate base is the substance that is produced from the acid losing a hydrogen ion. The conjugate acid is the substance that is produced from the base gaining a hydrogen ion. So here, Cl minus would be my conjugate base because it comes from the acid. And H3O plus would be my conjugate acid because it comes from the base. Cool? Let's do one more together. So NH3, I'm going to react that with water. What do we know NH3 to be? It's a base. You should know that it's a base. Okay. Next class, you'll be given other information to help you figure out if it's acidic or basic. But for right now, you should just know that NH3 is a base. NH4 plus was acidic. Yeah. All right, so if NH3 is my base, what does that mean water is? My acid. Has to act like my acid if NH3 is my base. So we're always transferring the hydrogen ion from the acid to the base. So in this case, water is going to give up a proton to my ammonia. So what are my products? And NH4 plus would be my conjugate acid, and OH minus would be my conjugate base. You cannot just say base, you have to say conjugate base to demonstrate that it came from the acid. Cool? All right, why don't you guys do C and D? We'll come back together and do E, but you guys can do C and D. You should be able to recognize that they are both what type of substances? Acids, because they begin with hydrogen. So I'm going to pause that while you guys do those 2 problems. So we did C and D. So for E, starting next class, you will be given more information about the substance that will help you decide if it's acidic or basic. For example, for these 2 acids that we did in C and D, you would be given the Ka values of them. And that's how you would know it's an acid, because you're given the Ka values. For E, I would give you the Kb value. I do not expect you at this point in your chemistry career to know by looking just at the formula that that is basic, okay, without giving you more information. Got it? Because some of those organic substances, it is difficult to tell if it's acidic or basic based off of just the formula. So by knowing that that's basic, when we add that to water, water is acidic in this case, what would our products be?
H, and then that thing. H in the organic molecule.
Okay, where would we put the I'm just knocking everything down. Technically, the hydrogen would go
In the front.
on the nitrogen.
Okay.
Like what we were talking about. So this is called like the condensed structural formula. In D, this is like the formula, like it's really, really condensed. Honestly, in the grand scheme of things, I'm not going to take off points if you put the hydrogen on the wrong end of the molecule. Okay? So, but I'm going to write it correctly because I care. So we would have CH3, CH2, NH3 plus, and OH minus. This first product is my conjugate acid, and my second product is the conjugate base. Cool? Do we feel confident with that? All right, so based off of the stuff we learned today, you can do up to homework 6A up to number 7, I believe. I think you cannot do the last 4 problems in homework 6A. Come on.